invariants for one-loop quiver with superpotential.
Yeah. Okay, thank you. Oh, that's strange. I'm guessing you can hear me, right? Oh. Great. Yeah, that's my talk, Motivic Donaldson-Thomas invariants with a one-loop quiver with superpotential. And here's my plan. Because the presence of the word motivic seems to cause unreasonable fear, we're going to start with just Donaldson-Thomas invariants for the situation that we'll end up working in. And I also want to talk about integrality, which is sort of the thread that goes through this talk and that makes this example interesting. Then for the second part of the talk, I suppose I should really have a stick. I will talk about just the motivic version of the first part, basically. Again, I'll talk about integrality. And it will turn out that in order to make sense of the integrality statement in the second part that is meant to induce the integrality statement in the first part, we have to talk about a couple of technical things, lambda rings and monodromy. The lambda rings come about because morally there's supposed to be some sort of categorification going on in the background. And when you decategorify a symmetric tensor category, you're meant to get a lambda ring, and that's where these lambda rings are meant to come from. And the monodromy comes from the fact that we're looking at this thing called the motivic Milnor fiber, which, just like the regular Milnor fiber, has some sort of action in monodromy. And then finally, I want to present the results. Okay, so okay, so I'm going to take a lot of background as sort of red. I'll hope that everyone knows what a quiver representation is. The quiver we're going to be interested in, and whenever you see this letter Q, is always going to be this, the one loop quiver. And I label the loop with an A. And we're going to be interested in moduli spaces of representations of this quiver. Understandably, there's not as much as usual to say about these things. I'll define the sort of A space of framed representations of this quiver of dimension vector n to be given by just endomorphisms of Cn times Cn. So you should think of this as basically a representation of this quiver, i.e., an n-dimensional representation of this quiver, i.e. an assignment of an endomorphism to the one loop, plus something living in the underlying vector space of that representation. As I say, I'm going to be interested in moduli spaces of such things, and these things really are going to be spaces in the sense they're going to be schemes. So in order to get to that point, I should impose some kind of stability condition. And again, this is probably pretty familiar to a lot of people in the audience. The stability condition is going to be that I restrict my attention to pairs such that V, G, V, G squared, V, ... are supposed to span Cn. Okay, and this, as I say, is just some stability condition. As it stands, this isn't a moduli space. I can change my basis of Cn and get what should be an isomorphic framed representation. And also, I left translate V along that change of basis. And I should get something that's an isomorphic framed representation, but it's coming from a different point in this space. So let me just make sure I get my notation right. So I'm going to denote by NC Hilb Q, 0, n. This really is going to be a moduli space, and this is given by taking the scheme theoretic quotient of this guy by grn. And this behaves very nicely as a scheme precisely because of the stability condition I picked, i.e. GLN actually acts freely on this guy. This is isomorphic as a scheme to the nth symmetric power of C, which of course is isomorphic in turn to Cn. And the reason for this isomorphism is that a point is, or a framed representation is determined by G, i.e. we can forget about V, which in turn is determined, by the eigenvalues with multiplicity. And this is precisely because of the stability condition that we've imposed. This stability condition ensures that all of the different Jordan normal blocks have different generalized eigenvector. And so that gives rise to this statement. OK, so there's meant to be a superpotential. And I'm going to pick a very simple one. So recall from yesterday, I think it was said yesterday, that a superpotential is meant to be a linear combination of cyclic paths in our quiver. Well, there aren't so many of those here. And in fact, I'm going to pick W to be homogeneous. So W is just going to be A to the D plus 1. And I'm going to define a function. Again, there's a question of notation here. This is a function on NC help Q0 n. And this function takes, let's see, the unordered n tuple z1 to zn. Well, it's got to be a symmetric function. And I pick this one, zi to the d plus 1. And again from yesterday, this is just the function that our superpotential induces on this guy. So once we pick this W, this is the function that we get on our ambient space. This is going to be our ambient smooth space. So W is supposed to impose some relations on the free path algebra of our quiver, given by non-commutative derivations of W. Well, everything in sight here is actually commutative. The free path algebra of this quiver is actually commutative. So the story here really reduces to something quite simple, i.e. W imposes the relation D plus 1 A to the D, i.e. A to the D. So what we're going to be interested in is our Jacobi algebra is going to be C A mod A to the D. So our Jacobi algebra, that says ALG. Our Jacobi algebra is just going to be this guy, who's finite dimensional. We want to look at moduli of representations of this Jacobi algebra. So let me just define things as before. Let framed MNW this time be, so it's pairs GV in end Cn times Cn such that G to the D equals 0, i.e. representations of this guy. But what I've written here is a little bit lax. This is I should take the scheme cut out by these equations. So I'm going to get some kind of non-reduced structure. Again, if I want a moduli space, I should take the open part given by, basically the same condition as before. I ask that my V in here generates the whole of Cn under repeated applications of G. And again, completely analogously, I define NC Hilb Q W N to be U N W mod G L N, and everything works as before. Yeah, sure.
So let's say if you take D equal to 2
Yeah.
and N large,
Yeah.
it will not be possible that V and GV generate all of Cn.
Yes, I know. The scheme will be empty.
Okay.
Yeah. So for large enough n, these schemes are empty. Yeah. Okay. So the point of our superpotential function on the smooth ambient guy is, as a rule, meant to be that the moduli space we're interested in occurs as the degeneracy locus of that superpotential function. So let me just write that up properly because it's important for what follows. I might actually use a different color because I'm kind of writing white on white. Okay. Is that better or worse or the same? Worse. So this, the moduli space we're interested in, occurs as a Zariski closed subspace of the smooth guy, Q. And what's more, it occurs as the scheme theoretic degeneracy locus of this function I defined up there, traits W. How was I calling it? M. And just a note on what the geometry here is. NC Hilb, I mean, yeah, it's kind of unfortunate there's this NC here. Maybe it shouldn't be here. But in general, everything is going to be non-commutative because quiver algebras tend to be non-commutative. It's just that this one really isn't. Then NC Hilb Q0N. This is, I mean, I write isomorphic. It's basically equal to Hilb NC, the Hilbert scheme of n points on C. And NC Hilb Q W N is isomorphic to the nth Hilbert scheme for spec of C A over A to the D. Okay, so to speak a language I don't understand, this has something to do with zero branes on C. Geometrically, I'm not sure how much independent interest it has. So let me try and motivate the situation by saying that the invariants we compute here will come up whenever you're computing Donaldson-Thomas invariants in a category where stable objects have one-dimensional extensions that are obstructed to some high degree. So for example, the theory that we work out here enables us to write out the Donaldson-Thomas invariants for 0 minus 2 curves, which might have a bit more independent interest.
So, I realize it's not in a language, but in the interpretation as zero branes on the affine line, is the stability condition the same as you get in physics? Do you have any idea?
Obviously, literally none.
Okay.
Yeah. Sorry. Sounds like that's something you could explain to me rather than me to you. Okay.
can you say what's the stability condition used in physics?
Well, if you've got some D branes, you look at the so-called D term, and you would see if the D term is putting some condition.
I see. And what is this D term?
I don't know. I'd have to work it out.
I see.
It might be the same thing.
Yeah. I can't. Okay, so right. I want to get somewhere near defining actual Donaldson-Thomas counts and then Donaldson-Thomas invariants. So the starting point is always, so this is now for a general quiver. When I want to denote a general quiver, I'll write Q prime and W prime for a general quiver with general superpotential. So this is going to be a partition function in one variable but with a multi-index, so really n variables, where n is the number of vertices in Q. And this is the sum over the a dimension vector, essentially, for Q of the integral over the non-commutative Hilbert scheme of something called, so I realize that some people will know what this is and some people will be maybe clueless about what it is. So I'll explain what this thing is meant to be. Sorry. So this is the integral over the moduli scheme of a constructible function, i.e. a function, in this case, to the integers, such that the preimage of any integer is some constructible subscheme, integrated with respect to the Euler characteristic. So a sort of less confusing way of writing this might be the sum over, and here's the indexing variable. A less confusing way of writing this quantity might be to write the sum n, an integer, of n times the Euler characteristic of the inverse under this constructible function of n. So it's kind of weighted Euler characteristic. I realize this is still completely confusing if you haven't seen this function before. And that's quite a long story. So let me just, well, I shouldn't call it a fact. I've already been reprimanded for calling this a fact, when it's obviously a theorem due to Kai Berendt. And it is that if a finite type scheme X over C, I also want it to be compact. If a compact finite type scheme X over C has what's called a symmetric perfect obstruction theory, then this quantity up here, but for X, so the integral over X of the microlocal function for X, which I still haven't actually defined, with respect to the Euler characteristic, is equal to this thing, which is called the virtual count. So these schemes with their symmetric perfect obstruction theories are things that come up in Donaldson-Thomas theory and Gromov-Witten theory, where you have some positive or non-zero dimensional scheme, which, due to sort of moral reasons relating to the deformation obstruction complex, should be zero dimensional. I should be countable, and this somehow morally is that count. And the point of this microlocal function is that actually it gives us another way of obtaining that count. And I should say that any scheme X has this microlocal function mu x and it's defined purely in terms of x. We don't need to know where x came from. We don't need to know that x secretly came from the study of a moduli space of objects in a 3 Calabi-Yau category. Any scheme x has this microlocal function defined for it. And if, in addition, that scheme x has a symmetric perfect obstruction theory and is compact so that we can define the virtual count, then that same number is given by integrating with respect to Berend's microlocal function. OK, so let me say something about integrality. So this partition function here, the Donaldson-Thomas partition function, this is just some a priori just some infinite partition function with coefficients in the integers. The integrality statement is that it has some quite special form. And it says that for general quiver with potential, I can rewrite this thing as a infinite product over dimension vectors, but non-zero. So that's a Q0, and that's a 0. 1 minus, and there are some things you need to get right. Minus 1's the V1, so this is the first component of the dimension vector. And I'll come back to why it's the first one and not some other one. X, V, again, V is a multi-index, it's a vector. All to the power of V1 times omega V. OK, so I've picked V1 because we're meant to be framing these representations. In the one vertex case, well, there's only one vector space that the framing vector can live in. In general, I'm just going to take the convention that the framing vector lives in the vector space living above the first vertex. And that's why V1 is somehow privileged in this. Let me also point out that if you take away this V1, and the conjecture is that these are integers, which I'm going to call the DT-invariants. OK, so if I were to take away this V1, this wouldn't be saying very much, but I'm not. I'm leaving it in there. OK, so this is a kind of mysterious statement.
Choose which vertex of your quiver potential is distinguished?
Say again?
Can I ask how you choose your framing? How do you if I give you a quiver potential?
Just choose one. And then call that vertex V1. And then this is meant to be true. Yeah, any choice. OK, yeah. OK, so I can already tell you the answer for our example. And it is that example Z.
Sorry, so the DT invariant depends on the choice of which vertex?
It should do, yeah.
Okay.
Yeah. In our example, there's no multi-index going on because, well, there's only one vertex. So I'm going to leave out the bar. And the answer is just 1 plus x to the d. So we can read off from this that in this example, omega 1 is d, and all the other omegas are zeros. So integrality is confirmed. So for me, the more interesting question is why do we expect integrality? And yeah, I'm going to have to just copy this down. The claim is going to be that for a general quiver with potential, our generating function is given by applying the Euler characteristic to a different generating function, which will have its own independent definition, which unfortunately is going to have to wait, where now the coefficients live in some naive Grothendieck ring of motives, hence the subscript MOT. And the integrality statement is going to follow from the special form that this is meant to take. And that special form is that Z, Q prime, W prime, MOT, I should X equals, and then this is something of a mess. Again, a product over dimension vectors, non-zero dimension vectors, of 1 minus, and then there's just going to be a slew of stuff which I'm going to have to explain. I want that to be V1 X to the B, and then I haven't left myself enough space here, times, well, to the power of blank, where blank equals L, this mysterious L over here, to the V1 minus 1, all over L to the half minus L to the minus a half, all times minus to the minus big omega of V. Okay. Is that legible? Or did you get it when I said it? It did some combination of, yeah, okay. Okay, so now there are some quite mysterious things on the board. Omega V, so, oh. Yeah, I don't know where those bars are coming from. Okay, so so let me first of all clear up what this thing is. L to the minus a half is a formal square root of a formal inverse to, well, unsurprisingly, L, the class in some naive Grothendieck ring of motives of the affine line. Okay, so that's that. And this thing, which I'm going to call the Motivic DT-invariant, is supposed to live, again, in some naive Grothendieck ring of motives. So this thing I'll denote K0, and I'll define it. Varieties over a point, and then some localization of that. So let me just throw this in. Okay, so I'll come to what this thing is, but you can already see, or maybe see, how applying Euler characteristic to this might give something up there. If I expand this out, I get V1 different terms, all of which have Euler characteristic minus 1. And if I take the Euler characteristic of some variety, then that is meant to be an integer. And so that is how taking the Euler characteristic of this expression is meant to prove integrality for me about the regular Donaldson-Thomas partition function. Okay, so let me try and define properly what this naive Grothendieck ring of motives is. So I'm going to jump straight to the relative version. So the naive Grothendieck ring of motives over Y is generated as an abelian group by symbols given by maps from I mean, there should be some conditions here. So let me just write finite type, or more ambiguously, nice, probably reduced. So it's generated by symbols like this, where this is just a map of schemes, but I mod out by the cut and paste relations. So I mod out by f restricted to u from u to y plus f restricted to v from v to y equals f from x to y, where u in x is open and v is its complement. Okay. Let me not at this moment tell you what the ring structure is. That's somehow a lot of the problem. Okay, but say I have something in this ring. I can take the Euler characteristic of the fiber above a point in y to get an integer. So in general, applying Euler characteristic to this ring, or at this point this abelian group, gives me a constructible function over y. And since, in this case, y is just a point, taking Euler characteristic just gives me a number, and more pertinently, an integer. Okay, and yeah. This statement, it will turn out, is only true if there is no monodromy. So this is the thing I'm going to end up talking lots about. Okay, so that's not meant to make much sense at this point. Okay, but although I've said some things explaining what's on the board, there's still quite a sort of basic and direct question, which is, say I have something in this ring, some polynomial with coefficients in this ring of this localized ring of naive motives. How am I supposed to raise it to the power of something else in that ring? How am I supposed to make sense of that? So that brings us on to part 3. And this somehow ends up being the heart of a lot of the theory here, which, as I say, is telling us something about decategorification. But that's a long story, which people have only really just started. So I'm going to mix up the terms lambda ring and pre-lambda ring. So when I talk about a lambda ring, I'm really talking about what a lot of people would refer to as a pre-lambda ring. Definition. A lambda ring structure on a ring R is given by a map which, slightly unconventionally, I'm going to call sigma, from R to the ring of formal power series in R. And just some notation, one writes sigma A equals the sum as, what am I using here? N. N goes from 0 to infinity of sigma superscript n a t to the n, and then, so this just defines this quantity for us. And then to sort of make a connection with what's written over there, one writes this instead as 1 minus t to the minus a. And that defines what this means for us. And this is supposed to satisfy some conditions. Those conditions are that sigma a equals 1 plus at mod the ideal generated by t squared. Sigma of a, what do I want? B equals a plus b. equals sigma A, sigma B. And thirdly, sigma 0 is meant to be 1. So e.g., let R equal the ring of integers and define, well, define sigma A equals 1 minus t to the minus A. I think I want to go for this. Okay, so that quite clearly defines a lambda ring structure on the integers. But then let me make the following observation. So what do we want to do? We want to define a lambda ring structure on this guy so that we can make sense of expressions like this. Let me just remark that the integers really live in this naive Grothendieck ring of motives over the point. This map is given by sending 1 to the class of a point. And what's more, 1 minus t to the minus n is given by the sum as I goes from 0 to infinity of the class of the ith, yeah, I want to get it the right way around, isometric power of n points. So if I consider a number n as a variety via this embedding, and I take its isometric power, I get another variety, but then I take it back, because again, it's just a collection of points. This gives the same answer. Okay, so this suggests immediately how to define a lambda ring structure on this ring, and it just works. So in general, define sigma of some effective class M to be given by the infinite sum I equals 0 to infinity of the class of the isometric power of M, all raised to the power of t to the I. Okay, and so this tells us what to do with effective classes.
So there you have I twice, so you get isometric power t to the I, but here you had this n points,
Yeah.
and then t to the I.
So if I were to put M equals n points.
Well, it's isometric power of n points. Oh,
Yeah. So this tells us what to do with effective classes, but then 2 and 3 actually tell us what to do with everything else. I.e. axioms 2 and 3. Okay. Okay. I suppose I can keep going here. So to recap a little bit, we have our Donaldson-Thomas partition function. It's supposed to satisfy some conjectural integrality property. And that conjectural integrality property is meant to come from applying Euler characteristics to some other property of Motivic generating series. But I still haven't actually defined what is this Motivic generating function. So that motivates this question: how to actually define this Motivic partition function. And the clue is that Barron's microlocal function, so this thing that we were integrating with respect to, this is given by taking the Euler characteristic of something called the Motivic vanishing cycle of trace W, where trace W is the superpotential function that exists on some ambient space. So let me keep things simple by just restricting our attention to R, Q, and W. So in our case, the microlocal function is given by taking the Euler characteristic of that function I had up on the board of trace W. So there'll be some n here. This thing is a relative motive. So this belongs to K0 of varieties over NC hilb NQW. Okay. In addition, given a relative motive, we obtain an absolute one. So given a relative motive, let me call it, I don't know, S, we obtain an absolute motive. Maybe let's give this subscript, maybe S. In the naive Grothendieck ring of motives over a point via push forward. Okay, so if I have some collection of maps from varieties into here, I obtain a collection of maps from varieties down to the point just by pushing forward along the structure morphism. And I'm going to denote the result of this operation by square bracket subscript ABS, ABS for absolute. I guess I can get rid of this. Okay, so this basically tells us how to do it. I'll come back to what this thing is as soon as I've got the definition of the Motivic partition function up on the board. So this is our independent definition, and this works for any Q and W. This is going to be the sum over dimension vectors again of, let me get this right, the Motivic vanishing function of basically the thing, the function on some ambient space whose critical locus is our moduli space. So in this case, trace Wn. But we want its absolute version to get something in the ring that I've just rubbed off the board, i.e. the naive Grothendieck ring of absolute motives. And then, obviously, I need mine. Right. So I need to define what this guy is. And that is, again, a long and difficult story, which I'm going to try and simplify with a conjecture. So let me start with a very unhelpful definition. So for f, a function from some smooth x to c, so x is smooth, this phi, oh crap, do I want, sorry, I always do this. It's my standard trick. Yeah. Phi subscript f is given by L to the minus a half the dimension of x times, and then, yeah, there are some sign conventions here. ZF, i.e. the motive of the well, the preimage of 0 under f. Well, let me just write that. F minus 1 of 0 minus, and this is why it's unhelpful, because I'm going to define it in terms of something equally mysterious. The motivic nearby fiber of f. I should point out that this the presence of this thing makes this somehow non-standard notation, but in a way that isn't terribly important. So this is meant to be the motivic nearby cycle of F. And the reason this is hard to define, well, if you consider, say, the Milnor fiber of some singularity, of some germ of some singularity, the point there is you prove at some early stage a theorem along the lines of if I restrict to a small epsilon ball of the origin in C and look at the pre-image, then what I get doesn't matter up to diffeomorphism. There isn't really a motivic analog of that statement. It doesn't matter how small I pick my epsilon ball, all of the motives within that ball could still all be completely different. So it's hard to define what is the motivic nearby fiber, except in special circumstances, which are basically the circumstances which go into the following conjecture. Okay, so let me get this right. Say x is equal to the product of y times c to the r. X is, everything here is again smooth. And say everything in sight, C star acts on everything in sight, acts trivially on y, and with non-negative weights on each of my factors of C, and also, and with a positive weight on a further copy of C, the image of F goes from X to C, and assume furthermore that F is equivariant with respect to this action. Then you can quickly see that, in fact, if I take any non-zero number here, the pre-image is isomorphic to the pre-image of any other non-zero number. So we can here define a naive motivic nearby fiber. The statement of the conjecture is that this motivic nearby fiber, which is defined properly by Denef and Lozer, is actually given by the pre-image of any non-zero number. Let's just pick 1. And what's more, this thing, so let me give this weight a number, and let me I seem to have picked S in the notes, which is unfortunate. This has an action by the S-th roots of unity. So this is, in fact, a mu S, where mu S is the group of the S-th roots of unity. It's a mu S equivariant absolute motive. This is the monodromy action, which appears in the original definition of Denef and Lozer. And the conjecture states furthermore that those mu S actions are the same. So they have a mu S action, we have a mu S action. And the conjecture is that they are the same. Yeah, I'm going to leave that. Okay. And this is actually partly a theorem. And I should say everything in this talk is joint work with Sven Meinhardt. Theorem is that the conjecture is true if all the weights on the C to the R part are less than or equal to 1. Okay. Okay, so given our definition of the motivic, the conjecture is true if all of the weights on the CR part are less than or equal to 1. Okay, so given the definition of the motivic Donaldson-Thomas partition series, we've now got a problem, because this partition series before was meant to have coefficients in just some ring of motives. But now we have some mu-s action knocking about. So once again, we have some difficulty in working out what to make of expressions like this, i.e. we have the difficulty of putting a lambda ring structure on the ring of mu-s equivariant motives. Or just on the abelian group of mu-s equivariant motives, since I still haven't given you a ring structure at all. Okay, so to summarize, we need a lambda ring structure on the naive Grothendieck, group of mu-s equivariant varieties over spec C. Okay, so when did I start? Did I start on the dot? 5 more minutes. Okay, that's probably all I need. Let me just tell you how this works. C star embedding in C is a C star equivariant map of weight S, just if I give both of these weight S C star actions. This gives us a embedding K0C, so this time of C star equivariant relative motives over C star. This embeds into this thing, which still only has an additive structure for us. So this is given just by pushing forward maps along this inclusion. Additionally, what do I want? C mapping down to spec C is again an equivariant map. So here, no weights. And this gives via pullback, i.e. via taking Cartesian products, this gives us a map the other way. So K0 C star varieties over spec C actually embeds into K0 C star varieties over something's gone wrong here. Yeah. Varieties over C. And the point is, this actually gives us a direct sum decomposition. So K0 varieties over C decomposes. So at some point, you have to lose the zeros. And this corresponds to, well, something minor, which obviously we don't have time for. So again, everything should be equivariant. Okay, C star equivariant varieties over C star plus K C star varieties over spec C. And this isn't the sort of obvious direct sum decomposition given by the fact that C decomposes into C star and a point. That's kind of the point of the construction. And then this should really just be a proposition. The left-hand side has a lambda ring structure, and it's given as follows. If I have X maps to C, and I want to multiply that by, so remember I still haven't even given you an actual ring structure. This we define to be just a sort of Cartesian product. But then we push it forward via addition. And sigma n of X mapping to C this, again, is sort of the natural thing. I just take sim n x mapping to sim n c, and then again I push forward via addition to c. So there's nothing very exciting or technical going on here, but the thing to prove is that this actually plus this descends to the thing we're actually interested in, which is going to be C star equivariant relative motives over C star, again, where this is being acted on by weight S. I should start to wrap up soon. And the reason we're interested in that is that there's an isomorphism between C star equivariant relative motives over C star, where this has an action of weight S, and the thing we're really interested in, which is mu S equivariant motives over the point. And the isomorphism here is, if I have something with a mu S equivariant, well, it's easier to take something in here. If I have something which is a relative motive over the torus, which is C star equivariant, I can go around the torus once and ask, what have I done to the fiber over 1? And that gives me an action of mu S. So that gives me my map going from here to here. And that's an isomorphism. And I guess I should just finish. The theorem, so all of the stage setting is just for us to be able to make sense of an expression like this in this new ring of new Grothendieck ring of varieties with monodromy action. And once we have the sort of tools to state the result, it's quite easy to prove. It comes out as follows. Um, 1 minus L to the minus a half x, and then the power is 1 minus mu to the d plus 1. So remember, our superpotential was a to the d plus 1. I consider this as a mu d plus 1 equivariant motive given by the action of this group on itself. And this is the answer. And this tells us, in this case, what the Motivic Donaldson-Thomas invariants are. They are as follows. If my dimension vector is 1, I get an L to the minus a half 1 minus mu d plus 1, and okay, I should finish that. But I'd just like to say that if you take the conjecture on trust, this is actually incredibly easy to prove. Indeed, it's almost definitional. And in fact, the conjecture, if it's not true, well, I think the world is a bad place. So this is a sort of nice example. And the first one where actual monodromy has shown up in any meaningful way. But yeah, I should really finish. So thanks a lot.
Are there any questions?
So in your example that you started with this x to the d,
Yeah.
Is the monodromy non-trivial or it's trivial?
It's non-trivial.
Non-trivial.
I mean, that is this example. So yeah, so if you just look at the Hilbert scheme for n equals 1, that Hilbert scheme has got to be just spec of your original ring. And that's given by the degeneracy locus of this function, the superpotential. If I want to work out what is this motivic vanishing cycle there, it's just it's the motivic Milnor fiber. So I'm looking at the motivic Milnor fiber of the function x to the d plus 1, and that certainly has non-trivial monodromy. And yeah, they all the way up you find non-trivial monodromy.
It translates this formula to the numerical case, so taking the order numbers.
Yeah.
You probably need the map, the order number from the Grothendieck ring.
It is. It is. Even with the monodromy, it is. certainly you need exactly that to get the normal integrality statement from the Motivic.
Let's thank the speaker again.